And welcome to the PE Civil Exam Review, Wastewater and Water Treatment. If you have any questions after this presentation, you can email me at awinfrey9@gmail.com. Here's a table of contents of the material we're going to cover today. I think in your Civil Engineering Reference Manual for the PE exam, there are two chapters. There's one chapter on water supply and treatment, and there's another chapter on wastewater collection systems and wastewater treatment. So we'll be covering most of those. When you look in the appendix, if you're going to be taking the environmental in the afternoon, at the end, I will be covering some of these at the end as we have time. This is an overall view of what we're going to be covering today. We're going to start out with the water supply, or the water intake from a reservoir or a river or whatever the water intake is. And we're going to follow that through a transmission line and be pumped from there into a water treatment plant. After the water treatment plant, some of the storage would be at the water treatment plant, but you could also have above ground water storage for fire protection and other purposes. After water treatment, if you look at the blue lines, it will go through a water distribution system, all the blue lines, which will feed the potable water to homes, businesses, and industries. And then the wastewater from those same sources, those same homes, businesses, and industries, will go through the red lines or the sewers and will be collected and routed to the wastewater treatment plant and then back into the wastewater receiving stream. So we'll be covering aspects of the water treatment, the storage, the force mains for water distribution, also the sewer lines, and the wastewater treatment. First of all, you have to know a little bit about the Clean Water Act and the overall objective of the Clean Water Act. There are 5 goals for the streams and lakes to make sure that we have protection of aquatic life, primary contact recreation, swimming, secondary contact recreation or wading, fish consumption, and of course for drinking water. The states, as well as EPA, and it's usually left in the hands of the states, determine the total maximum daily waste load that can enter a body of water, either a lake or stream from a wastewater treatment plant. And also the states do surveys to make sure that the streams can handle wastewater effluents. And that would include, they do a surface water quality evaluation. They check the bacteria, the habitat, the algae, microinvertebrates, and the fish in the streams. The Clean Water Act has set the standards for the nation. And those are 5-day BOD, which I'll go into in more detail later on. And to have a wastewater treatment plant has to have minimum levels of 30 milligrams per liter of 5-day BOD or less. Can't have over 30. Same with total suspended solids, 30 milligrams per liter. The pH should be between 6 and 9, and the removal efficiency of the basic wastewater treatment plant or secondary treatment plant has to knock out 85% of the BOD5 and the total suspended solids. As far as water treatment plants go and wastewater treatment, both require permits from the state. Both have to be protected from 100-year floods, and both have to go through a public participation process. Sometimes this is on the test. NIMBY is involved as part of the public participation process when citizens do not want a wastewater treatment plant near their property. And this is called not in my backyard. Sometimes that's actually a question on a test. Wastewater treatment plants. They have to be located downwind and away from residential areas. They're usually located at the lowest elevation to promote gravity flow. And they're located downstream from the city, the municipality's water treatment intake. And the discharge at the approved stream location and with approved treatment has to be approved by the state. For water treatment plants, they're located near an acceptable water resource, and the state has to approve the intake quantities that the city or source would be taken out of the lake or the river to make sure they do not deplete the water supply for that lake or river. And the water quality of the intake varies significantly with the weather, which affects the operation of the water treatment plant. So in summary, for the wastewater treatment objectives by the Clean Water Act would include effluent limitations of BOD5 of 30, total suspended solids of 30 maximum. Others that are controlled are pH, organics, toxicity, and chemical oxygen demand. The water treatment objectives for the coming out of the water treatment plant that would go to the water distribution system and into your tap for drinking water should have zero fecal coliform and pathogenic bacteria, insignificant solids or very low turbidity, no taste and odor problems, insignificant organics, and it should be noted that bottled water is not regulated by EPA, but it's regulated by the Food and Drug Administration. For references, two things I recommend, and you do have a one-page for wastewater. I didn't notice anything for the water treatment, but you can go on the internet and look up the 10 state standards for water treatment, and also the 10 state standards for wastewater treatment. They're two different documents that are about 70 or 80 pages long. You don't have to copy everything off. And you may want to tell you if you want more information or get into more detail in this topic, this is the best reference, and these are actually in the Civil Engineering Reference Manual as a reference, but there's only about one page. It's just a summary. Okay, we're going to start with water treatment. We've already drawn water from the water supply, and we have to start looking at design. The average daily flow, it's based on 165 gallons per capita per day. The peak flow is normally 2 to 3 times the average daily flow. And here's how the 165 gallons per capita per day was derived as an average flow. The domestic is less than half of that total. You can see it's only 70. Commercial is 25, industrial 45, public 15, and losses in the system would be 10. And it should be noted that each city is going to vary because you may have a very small city with a very small population that has a large industry, and the industrial could be much more than what the domestic would be. This is a typical flow diagram for water treatment. As I said before, we start from the water supply from the stream or lake. It goes through a bar screen, then a mixed tank, a settling tank. This is usually called a primary settling tank. Sometimes the mixed tank and settling tank are one, where you would have aeration that would mix the chemicals instead of having a separate mixed tank. Then you'd have a final settling tank or a clarifier. It goes through sand filters or rapid filters, and then it's chlorinated, and then you have the water goes out into the water distribution system. Now, for purpose of the people who are taking civil engineering in the morning, you could have some questions dealing with the quantity of water flow that is going through any of these units. but you're probably not going to have a lot of questions dealing with the chemistry involved, which is covered in the appendix. Water supplies have to meet all of these criteria, and the state has to approve the water supply for use for municipal drinking water. Even before it's treated, they have to approve, make sure that there's nothing there are no chemicals or materials in that water supply that would go through a water treatment plant and cause a health problem. Okay, the bar screens are mainly, you're pumping from a lake or a stream. The bar screens are to knock out the large fish and twigs and branches that may get into the water treatment system and cause a problem. Okay, the mixed tank. And all the data I'm giving you in these summary sheets for each of these unit processes is based on the 10 state standards, and that's what is normally on the test, and that's what you have in your civil engineering reference manual. Chemicals are mixed, added to the mixed tank, and it's for a detention time of 30 to 60 seconds to make sure that the chemicals are mixed properly. Calcium carbonate is added for coagulation and pH adjustment. On a normal dry day when the water is clear at the supply, usually only the lime or the calcium carbonate has to be added. After a rainfall period, usually as much as 10 days or 2 weeks after a heavy rain, then you would also add aluminum sulfate to knock out a lot of the solids, and also activated carbon to knock out taste and odor problems. The mixed tanks are usually cylindrical. You have a motor at the top. You're feeding hydrated lime or alum. You would have a couple of small tanks at the top where you would put the hydrated lime and alum and make a slurry out of it so it's easier to feed and it mixes better. The raw water would come in on the bottom, and these are just mixing paddles, and it's mixed for 30 to 60 seconds, and it goes out of the mixed tank into the settling tank. So how do you design a mixed tank? If you have a city of 5,000 population and a peak flow of 165, now I'm given a peak flow of 165. Sometimes if they say the peak flow is a factor of 2 or 1.5, then you would have to multiply that 2 times the 165 because the 165 is the average design flow. But if they give you the peak flow outright, then you just go with the 165. So the flow, or Q, is equal to 165 gallons per capita per day times the population. So you multiply those together, you get 825,000 gallons per day. The formula for the volume of the mixed tank is the flow times the detention time. So the flow is 825,000 gallons per day. I'm going to go ahead and use a 1 minute detention time. It could be 30 seconds to 1 minute. Usually they'll tell you what it is on the test, what the detention time would be. And then you convert the minutes to days, so the gallons per day would cancel out. Come up with a total of 573 gallons. Remember, mixed tanks aren't very large compared to the other units because it only has to stay in there for a minute. So the volume of the tank would be 573 gallons times there's 7.48 gallons per cubic feet. So you get a total of 77 cubic feet for the mixed tank. If they ask for the size of the diameter of the tank, it's going to be a circular tank, and the height of the tank should be about 2 times the radius. And the reason for that it makes it more of a total cylinder, even though it's a circle rather than a cylinder. So We have the volume of 77 cubic feet. If we want to find the radius, we set that times the radius times 2 times the radius for the height, and you come up with R equal 2.3 feet, and the diameter in the height would be twice the radius would be 4.6 feet. Okay, for a city of 5,000 population, how much alum on average is required per day in pounds if concentration is 10 milligrams per liter? Now, even though this is a chemistry type problem, sometimes they may ask this in the morning, and you can use the equation of if it's any chemical you add, whether it's alum or lime or whatever, you take 8.34 times Q in MGD times C, or the concentration. So that's the formula that would be used over and over again. So we know that the Q is 825,000 gallons per day. We got to convert that to MGD, 0.825. Concentration is 10, and you come up with 68.8 pounds per day. So this is a shortcut way to, without going through a lot of conversions of milligrams per liter to gallons and everything else to get everything canceled out. This gives you the right answer every time. Now the settling tank. The settling tanks have a surface loading rate that would be the total exposed water surface on the top of the tank of 600 to 1,000 gallons per day per square foot. The length of this tank is usually 3 or 4 times the width. I'm using 4 times the width here, and the depth of the tank is normally 10 feet. Usually if you get a depth of more than 10 feet, then you're going to hit solid rock in a lot of places, since a lot of the water treatment plants are near the water source. Or if you have a depth greater than 10 or 12 feet, then people have to get down and clean out these tanks. And it would be dangerous and difficult to clean them out if you get the depth too much. So what are the dimensions of a settling tank for a 1.5 MGD plant? The formula for that is the surface area is equal to the flow over the overflow rate. And the overflow rate is this 600 to 1,000 gallons per day per square foot. So we know what the flow is. It's a 1.5 MGD plant. The overflow rate, I'm going to use 1,000, use the upper end of the range. So the surface area is 1,500 square feet. Now, to get the dimensions of the tank, the length is always 4 times the width, 3 or 4 times the width, whatever they specify. So you'd have width times length, 4W, or 4W squared equals 1,500. And you solve, and you have a width of 19.4, a length of 77.5, and a depth of 10. We're just using the depth of 10. Now, in this case, if you're doing the engineering drawings for somebody to build a plant, you would use a width of 20 feet and maybe a length of 80 feet. You're not going to use something that's 19.4, because if you use a standard width, a lot of these things are, if they're concrete and it had to be poured, you can get the forms in standard dimensions that would take care of 20 and a length of 80. Okay, the clarifiers. The clarifiers have real light, small particles, because the heavier settled particles, the heavier particles would have gone and would have settled out in the settling tank. So the floating or suspended solids would be real small particles, and you usually have to add something to get these particles to settle. Usually you can add alum or a long chain polymer. And for this tank, we're going to use a settling rate of 1,400 gallons per day per square foot. Now, the depth of the clarifier, sometimes this is pumped up into a clarifier. The depth could be 10 to 30 feet, but a lot of times you'll have a hopper bottom, And I'll show you that in another picture. So what is the radius of a clarifier for that same 1.5 MGD plant? The surface area Q, we're using 1.5 again. The overflow rate, though, was changed to 1,400. So we get a surface area of 1,071, and it's a circle, so solving for the radius, it would be an 18.5 foot radius, and of course we'd use an even number of feet. Yeah, the surface loading rate is the same as the overflow rate for purposes of plugging them into the formula. They're just called different different names. Okay, filters. Sand and other media filters are used to remove suspended solids. The slow sand filters I don't prefer because the water tends to float in there, and it takes too long to filter it out. So a rapid sand filter is what I would prefer at 4 gallons per minute per square foot. Okay, for a city of 5,000 population and a peak factor of 2. Now here you see the peak factor is coming in. And they would almost have to give you the peak factor because if you notice in the back criteria, the peak factor can vary quite a bit for water. Okay, so we're starting out with a population of 5,000. We have to get that to gallons. So we have surface areas equal to 5,000 population times our average design flow of 165 gallons per capita per day times a peak factor of 2. So that gives us our total flow there. Then we're going to divide it by 4 gallons per minute per square foot. And we have, since this is not in gallons per day, we have to convert the minutes to days, so the days will cancel out. You should keep, the sand filter should have a depth of a minimum of 3 feet to prevent breakthrough of solids through the bottom. Okay, the chlorinator. The chlorinators have to add enough chlorine to provide a residual chlorine to eliminate waterborne pathogens. Some people say, well, what about it? A lot of plants use infrared light, or they use liquid oxygen instead of chlorination. Well, basically, you have to use chlorination somewhere. If you use any type of infrared to knock out the bacteria, that does not leave a residual. So you still would have to have chlorinator after that. Okay, I'm going to go back to this. As far as rounding, you're looking at, if they're giving you the numbers, you have to use your rounding basic principles. Rules. You have 5,000 population, 165. So you can use significant digits. I usually round it off to 3 significant. I don't use decimals. I never use decimals. But if this gets into a real large number, I would round it off. But for a smaller sand filter or something else, you need to be a little bit more accurate. So it depends on what formula you're using that in. And where did the 4 come from? Back here, rapid sand filters have surface loadings of 4 gallons per minute per square foot. Okay. Now let's look at how much chlorine you add. Now we're going to use the same formula for calculating that. That's here at the bottom. Whenever you add a chemical, chlorine, lime, or anything else, you're going to use the 8.34 times the Q in MGD times the C in milligrams per liter of part per million. So in this case, first of all, we have to find out what the Q is. So for a peak design flow of 1 CAF, what is the volume of the chlorinator? So we're going to find the volume first. So we're going to use Q equal T detention time, and we're using. Let's go back. It depends as far as the detention time. It depends on how dirty the water is, but normally you're going to have a detention time of maybe 10 minutes up to 30 minutes, sometimes longer. So I'm just using an average of about 20 minutes, and you come up with 1,200 cubic feet. Okay, how many pounds of chlorine would be added if the concentration of the chlorine is maintained at 2 milligrams per liter? So you have, first of all, we have cubic feet per second, and then this formula requires Q in million gallons per day. 1 cubic foot per second is equal to 0.643 million gallons per day. That's your conversion. So all you have to do is plug in 8.34, which is the constant. Q in the million gallons per day, 0.643, and then the 2 is 2 milligrams per liter. That's your concentration. And you come up with 10.7 pounds per day. The depth, going back to the sand filter, we use a depth of, it's required that you have a depth of at least 3 feet because the solids would break through if the depth were only 1 foot or 2 foot. So they've determined, it's been studied and everything else, and you need at least 3 feet depth of sand to keep the solids from breaking through. Okay, after you treat the water, after it's chlorinated, it's going to go to storage. And usually it goes to an elevated storage tank that would be located across town at a higher elevation from the water treatment plant. And there's a reason for that. This kind of shows everything together where you have the water treatment plant, but you have to get some, you have to have an elevated storage tank. Let me show a better picture on that. Okay. Your treatment plant would probably be on this side of town. Let's say if this is north, the northwest side of town would be the treatment plant. Storage tank would be on the opposite side of town on a higher elevation. This allows you to have, you could have fire protection and also supply of water in the case of emergency or basically just everyday water. The treatment plant here, you can keep the pressure up for halfway across town or more, but it would be very difficult to keep the pressure up all the way across town, so you'd have a storage tank here, especially for fire protection, that would give you pressure, adequate pressure that would cover this half of the town. So if there were a fire over here, it probably, this half of the town, you'd probably use the treatment plant because you would have pumps there if there were adequate. If the fire's on this side of town, you'd probably use the storage tank. Sometimes there's a question on the test dealing with storage tanks. And what capacity, water tank in gallons would be required for a population of 1,000? Now, normally, if you don't know what the population water use is, because there may be a lot of industry, this may be a small, in this case, this is a small town that doesn't have a lot of industry. So 70 gallons per capita per day is the average water use. So, but if you don't know that, you'd use a peak factor of 3 times the peak hourly flow and 20% of the peak hourly flow for storage. In this case, for the population use for storage, population use would be population times 70 gallons per capita per day. So this is a small town, and the average flow going through that town is 70,000 gallons per day. So that's what's going to be used for population. Now, a lot of times they'll just give you that, they'll give you this number. They said a city uses an average of or a peak of so many gallons per day. And then after you have that number, you go to the fire protection formula. The fire protection formula has been developed by insurance companies across the United States to make sure that you have adequate water supply for any type of fire emergencies. So the formula is is 1020 square root of P times 1 minus 0.01 times the square root of P. In this case, and the P is in thousands. Population is in thousands. The P is population is thousands. So to get Q, you just plug in 1 for the population in the above formula, and that gives you a total of 1,009 gallons per minute. Now, to get the flow rate that's required, whatever number you come up here in Q, you have to divide it by 1,000. And 1,009 divided by 1,000 would be 1 hour required. Now, here's another rounding thing. If it's a higher number, you can round it up to 2 hours. But then to get the total storage you need, since you need 1,009 gallons per minute, you need that for 1 hour, or 60 minutes an hour. And you come up with a total of 60,540 gallons per day. Now, the water tank capacity could be one of two things. Sometimes, if the treatment plant goes down, you want the storage tank to handle the average flow of the city, which is 70,000, plus the fire demand, which is 60,540. In this case, the city wanted both. If they only asked for the fire demand, then it would only be 60,540. Somebody asked if this 1,000 was the population. No, this is just part of the insurance formula to determine how many hours are required. And that would be plugged into this formula down here. Okay, water distribution. So after the water is treated and after you have adequate storage, then it goes into the water distribution to the homes, the industries, the schools, etc. Now, for water distribution, you have to look at networks, and we don't have time to go into all the different calculations for networks, but there are some basic questions. What is preferred? And if you look at your civil engineering reference manual, especially on the wastewater treatment, usually there are definitions that are given in there. There are a couple of pages of definitions, and they have appendices in the back that you need to be aware of. Because sometimes some of the questions are qualitative, or they just want a definition. But for networks, if you have a water supply, if you have water that's treated and you want to distribute the water to these different subdivisions, each of these nodes would represent a subdivision, or an industry or a school or something like that. If you have this type of system, you have a safe, this is called a loop system. You have a safer system than this system. Let's say if you want to minimize your piping, you'd put in this type of system. And I've seen cities put in this type of system. But what happens if you have in this system, if you have a pipe break here, you cut off 1, 2, 3, 4 areas, or 3 subdivisions, or 4 industries. So if the break there, you cut all these off, you're still able to provide these 4 over here. With this type of system, if you have a break and it's looped, nothing is cut off. You can see with the loop system, if you have a break up here, you can still supply the entire city. So in water distribution, you have to look at how the pipes are laid out and make sure you have a loop system. And this wouldn't be for small distribution lines. This would be for the larger lines. Okay, 10 state standards, I've kind of summarized these for you, so you can go back to that reference. You can look on the internet at the 80-page book. But I've given you kind of summary. The water mains are usually, they're force mains. They're 3-inch diameter or greater, and you have to have a minimum velocity of 2 feet per second. For water main for fire protection, the fire protection lines have to be a 6-inch diameter minimum force main. And you have to have a minimum pressure of 20, a working pressure of 60 to 80. And we're going to get into some problems dealing with these working. Okay, the valves are 500 feet or less apart. And for other property, that's for commercial properties. For other properties, they can be as far as 800 feet apart. The valves for rural roads are less than 1 mile. So you can't go over a mile without having valves for the distribution system. Fire hydrants, usually 350 to 600 spacing. And the minimum water storage at a treatment plant is the average daily consumption. I went over that before. So the minimum water storage has to be the average daily consumption. And air relief valves are at high points as necessary. Okay, these are just a couple of tables I threw in there, and I marked out the top of it, but these are force mains. And for water lines, the force main has to be 3 inches or larger. But this just gives you an idea. You may have a problem on the test where they would say if you have a velocity of 10 feet per second and an 8-inch line with a certain head loss or whatever, they may not even give you the head loss, what is the maximum flow that that line can carry? Well, you can get in this table and you can check your answer out. If you work this out, which we'll work out later on, but you can use a table like this to see that the maximum that an 8-inch line can carry at a velocity of 10 is 1,600 gallons per minute. Okay, here's another force main table where remember that for force mains for water, the velocity has to be a minimum of 2 feet per second. But let's say your velocity is not 2 feet per second. Let's say it's 4 feet or 6 feet per second. Well, an 8-inch line here would be able to carry, at 2 feet per second, it would carry 313 gallons per minute, 4 feet, 626, and then 6 feet, 626. You can see it doesn't, an 8-inch line, even though the velocity increases, it doesn't carry over 626. Now we're getting into pump stations. You have to have pump stations to pump the water through the water distribution system, through the force mains to get to the house, and the pump stations have to provide adequate pressure. And there are a number of formulas that deal with pump stations. And this could be a whole course. And I'm going to give you the basic formulas. Some of these formulas aren't given in books, so it's worthwhile writing these down or having these at your hand. But the efficiency of the pump is the you have the water horsepower divided by the brake horsepower. Okay, and don't worry about what the definitions are. You may have to look some of those up later on. But the water horsepower, which is a key thing, is equal to the Q, the flow, times the height divided by 3956. So that's a shortcut formula to get the horsepower of a pump. Okay, I'm going to go back. So there are a lot of questions dealing with the 1,000 population, 1,000, the 1,000, the 1,009 divided by 1,000. 1,000, the denominator, is a formula, is a constant in the formula. It's not the population. Okay, here's a bunch of formulas that we're going to go through. We're going to go through a problem on each one of those. Horsepower is very important. They may ask that. If they ask for the flow, and you know the horsepower of the pump divided by the head, then here's the other formula. If you want to calculate the head, you know the horsepower and the Q and so forth. The pump efficiency, water horsepower divided by the braking horsepower. And the braking horsepower is 100 times the flow in the head divided by 3960, and N is the efficiency at the top. So that's how you calculate braking horsepower. So pumps are pretty complicated, but and if you look, a lot of people won't even try to work these, but if you have these formulas on hand, you can get the right answer pretty quickly. Okay, the system curves or pump curves. This is just some definitions here where I'm going to go straight ahead to the pump station curves. Let's say you have a reservoir here and you're pumping straight across to another reservoir, and both heads are the same. You have the same elevation on the top of the water here. Then you would have, it would start out on the left side, this is the important thing. On the left side, the head would be 0 if everything's at the same elevation. You have the same elevation there, same head elevation there. So you'd start out at 0, and to pump a certain amount, the flow rate, depending on what flow rate, the curve would go up like that. Now here's another one where you have a difference in the elevation of the water, and this is called a static lift. And this difference on the pump curve would be this distance on the curve. That's your static lift. Say this is 50 feet, then you would have a chart over here that would be 50 feet. You'd have a straight line across there, and then you would have the curve. It wouldn't start out at 0, it would start out at 50 feet. So that's the second example. The third example, let's say you're pumping basically downhill where you have a negative static lift. So you can see that if this was 50 feet again, this would be minus 50 feet on the curve. That 0 shouldn't be there. The 0 would be here, this would be a negative 50, and then you'd start the curve based on the size of the pump. So those are 3 different alternatives. People have said they've given graphs on them, and they may just say if you have a certain static lift, or they may have a figure like this. You have to count, is it a negative static lift, is it a 0 static lift, or a plus? Then the curve would look like it'd either be below 0, at 0, or above 0. So those are the 3 options for developing part of the pump curve. Now you could have 2 different static lifts in a branching pipe, and here you're starting out here, and you can see the pump is going, some of the water is going up to this one, the other water is going up here. So you have this elevation and that elevation, that would be static lift number 2. Here's static lift number 1. Okay, static lift number 2, that would be that distance, and then static lift number 1 would be that distance. And then you would have a pump curve. The curve would come in here, and then you'd have a combined curve. You're not going to have anything that complicated with it. Okay, you could very well have a problem like this, and it looks complicated, but if you look at it, it's basically Q equals VA. What size force main would be required for the below figure in data? Okay, the required minimum force main has a velocity of 2 feet per second. That's from the 2-state standards. The conversion factor for cubic feet per second to gallons per minute is 448.8 gallons per minute for each CFS. Q is equal to A VA, and A, we're solving for the area of the force main, is equal to Q divided by V. So Q divided by V, we have 374 gallons per minute. That's this Q right here. The Q is given right here in the figure. So you have 374 gallons per minute that's pumped uphill. Okay, so there's 374. So we want to convert that to cubic feet per second, so we multiply it by 1 cubic feet per second over the conversion factor. And then we want a velocity of a minimum of 2 feet per second. So we're just going to plug in 2 feet per second there as the velocity, minimum velocity. So we solve for the area, and we come up with 60 square inches. Okay, 60 square inches, plugging it into the formula for a circle. The radius of the pipe would be a 4.37, and the diameter would be 8.74, an 8.74 inch pipe. Okay. Now, what I'm going to do, pipes don't come in 8.74. They come in, 8 inches, 12 inches, whatever. They don't come in an odd number like this. So I'm going to use an 8-inch pipe. And if I use an 8-inch pipe, it's a smaller pipe, it would give me, it would have to be a larger, a different velocity here. It has to be a greater velocity since I'm using an 8-inch pipe. Okay, so V for an 8-inch pipe, we're going to plug it in the same formula, but it's going to be Q over A, the area of an 8-inch pipe. And 8-inch pipe is 4 inches divided by 12 to get it to feet. And we come up with a velocity of 2.39 feet per second. So that would be the velocity. Okay, other things you see here is you see that the pump elevation is 100 and the invert elevation is 150. So the static lift is 150 minus 100. So this distance right here is 50 feet. So you got to remember that's 50 feet. The length, the horizontal distance is 2,000 feet. So we're going to use Hayes and Williams and use that for force mains. And some of these formulas aren't given in textbooks. Usually you get this formula, but here's Q. If you drive for Q, you'd have this formula. If you want to get the diameter of the pipe directly, you would just plug it into this formula. Okay, this is a Hayes and Williams graph. It's a very useful graph, and we're going to work a problem plugging into the formula and then check it by going back to this graph. So, first of all, we want to know what is the total dynamic head. All right, the static head from the figure that I showed you, remember it was 150 to the top of the hill. The pump was at 100 feet, so the static head difference, the static head is 50 feet. The velocity we calculated for an 8-inch pipe is 2.39 feet per second. Okay, the friction loss using the green curve intersect with the middle line and C equal 100 is 4 feet per thousand. Okay, let's go back to that curve. Okay, we're going to start out here with a green line, and the discharge in gallons per minute was, go back to that, the discharge was at 375? Yeah, 374 is the discharge. So discharge in gallons, start here with 374, and then it's an 8-inch pipe. So you draw a line through the 8-inch pipe. There's a 6-inch, there's an 8-inch. Draw this green line through the 8-inch pipe. You come up to this pivot line, and we're still following the green line. And we want to go to the velocity, which is 2.39. So we pivot here, draw a straight line to 2.39. Okay. So you can see that you can come up with, if you know you're putting in an 8-inch line, or if you know the velocity and you know the discharge, you can just draw a line from whatever your discharge is to the velocity. That would give you the size of pipe you need. So you wouldn't have to work through that formula to get the 8-inch pipe. Now at this pivot line, the green line, Let's go back. I'm going to go back here. Getting ahead of myself. Okay. Friction loss on the chart using a green curve intersection with the middle line and C equal 100 is 4 feet per 1,000 feet. So we have, go back here. Okay, here's the friction loss of 4. And we're going to use the value of C equal 100. There's a C equal 100. So we go back to this pivot line on the green line. It goes to the C value of 100, and the friction loss is 4. That's the loss of head in units per 1,000 units. So since we have a length, the horizontal length is 2,000 feet, so the friction loss is in thousands, 2 times the 4 from the chart. It gives you a friction loss of 8. Now to calculate the velocity head, the velocity is 2.39 squared divided by 2 times gravity, 32.4, and it's 0.088, which is pretty much insignificant. So it would be 8.1 if you want to go that far. So your total dynamic head, the total head is what you need. Static head is 50. The total of the friction loss, 8, and this one gives you 8 feet, rounded off. So you have a total dynamic head, H, of 58. Now, what is the operating pressure of the pump station? This is simply P is equal to 62.4 times the total dynamic head. You have a total dynamic head of 58. That comes up, gives you pounds per square foot. You convert the pounds per square foot to pounds per square inches. So your operating pressure is 25.1 pounds per square inch. What is the horsepower? The horsepower is QH divided by 3956. That's from our formulas. You have a Q of 374. Calculate a head of 58, so the horsepower is 5.48. Now here's a case where you have, let's say you have a pump here, you're pumping uphill. So you have a 50-foot static, so your curve is going to go, your horizontal line or the 0 point on the y-axis will be 50. And then your head plus friction loss would be this curve. Then this is a pump curve for a 5 horsepower pump. It's kind of shaky here, but this is based, you just have to test, each pump is different. So usually you get a bunch of these curves and you determine what size you want. But the intersection of your of this curve and the pump curve basically gives you the flow rate that you need for the pump. Okay, what should the wet well capacity be in gallons? And the wet well handles the water as kind of a mini storage tank, and because you can't run the pump continuously or you wear the pump out. So basically, you design the wet well to handle so much water so that the pump is only pumping part of the time. And the volume of your wet well in gallons is TQ divided by 4, where T is in minutes. Now T, it shows that you're only going to pump 10 to 30 minutes. You're not going to pump over half the time. Okay, the volume. Now we go back. If the braking horsepower, let's go back and see what the braking horsepower was. Guess we didn't calculate the braking. There it is. Okay. If you calculate the braking horsepower, assuming that the pump efficient is 75, you come up with a braking horsepower of 7. So if the braking horsepower is less than 20, then you use 15 minutes. So this is less than 20, use 15 minutes. This braking horsepower came out to be 80, then you would use 20 minutes. If it came out to be 100 or greater, then you'd use 30 minutes. So we're going to use 15 minutes based on the braking horsepower times the flow, 374, divided by 4, and it's the wet well capacity would be 1,403 gallons. Someone asked, how do I know that C is equal to 100? And that depends on it depends on the type of pipe you're pumping in, and usually the force mains you use about 100 for the coefficient for force mains for water distribution. Okay, wastewater collection. I'm getting a lot of questions, and I'm not sure if I want to make sure I get through all the presentations. So if you still have a question and I can't get through it at the end, be sure to email me. Okay, wastewater collection systems. We're going to use the 10 state standards. Now, for gravity sewers, the pipes have to be 8 inches or larger. Now, the gravity sewers, these are not the lines that come from the house to the street. These are the lines that are actually in the street. Okay, so for the gravity sewer would be 8 inches, and those are the lines that the city or the county would maintain. They don't maintain the line from the street to your house. The force mains have to be 4 inches in diameter because you have solids involved, and for water treatment, it's only 3 inches in diameter. Again, the minimum velocity, the velocity has to be greater than 2 feet per second. Hayes and Williams would be C equal 100 for unlined iron and steel. That may answer somebody's question. Why did I use 100? Because most pressure lines are going to be iron or steel, and I'm going to use 100 for that. For the PVC lines, you're going to use 120 or less. You have to have a 10-foot separation from the water lines, and this is you have to have 10-foot separation from the water lines and the sewer lines. There have been cities a long time ago that decided to save money, and they put the sewer line in the same ditch as they put the water line. Of course, the pressure line would suck in water, and the sewer lines leak, so you'd have cross-contamination there. So the water and sewer lines have to be at least 10 feet apart. Manholes, about 400 feet for 15 diameters or less, 500 feet for 1830. Lift stations, you have to have at least 2 pumps. Wet well will not exceed 30 minutes for each tee. Okay, this is what a collection system looks like as opposed to a network for a water treatment system. Here's design number one. Some engineers that haven't done a lot of water design, they may try to do this where you start, let's say this is a subdivision, and let's say that the land is pretty level. Let's say the topography is basically level for this subdivision. So if you start here with a line for your collection system in the street, and you run it all the way down to this end before you get to a main or a sub-main, which is the blue line, then you would have to get the flow you need for sewers, gravity flow. The depth of the sewer has to be deeper and deeper as you go down here. So once you get to this point, you're going to have a pretty good depth. Now, another way is to make it, instead of having your main line on one end over here, is let the main line go in the middle. And since the land is fairly level, you would have gravity flow going to there, gravity flow going to there. So the depth of this at this point would be half the depth that you would have over here. So it's better to make sure you place your mains and sub-mains so you minimize the depth or length that you'd have to carry the line. For interceptor or trunk line, you use a 2.5 peak factor or 250 gallons per day. For a main or sub-main, 2.5 peak factor or 250. And for collectors, you use 4 for a peak factor of 400. Okay, now I'm going to show you charts. I showed you charts for force mains. This is for gravity sewers. You can see that an 8-inch line gravity sewer would have to have a minimum slope of 0.4 feet per 100 feet. But if you get up to the larger line, like a 3-foot line here, the minimum slope would only have to be 0.046. The carrying capacity of the gravity sewers. Here's the gravity sewers. Remember that for the cities, 8 inches, this 8-inch diameter is the minimum. Even though some houses, the sewers from the house to the sewer may be as low as 3, 4, 6 inches. But the engineering design would normally entail the 8 inches or larger. And here's your slope and decline per 100 feet. There's 1 foot per 100 feet up to 36 and 100 feet. So this would give your flow for an 8-inch pipe. It would be 153 for a slope of 1 there, and for a slope of 2, it'd be 211. And on the steeper you get, the more flow you'd have going through the pipe. Okay, the gravity sewer, and you probably, I don't know if you've had Bhaskar or not yet, but he was supposed to cover stormwater and flow through channels, etc. We're talking about flow through force mains and pipes in all cases. So the hydraulic radius, the ratio of the area in flow to the wetted perimeter, the hydraulic radius is equal to the area over the wetted perimeter. So here's a pipe that's flowing half full, and the wetted perimeter would only be half of the circumference. So for a circular pipe flowing full or half full, the hydraulic radius is equal to D over 4. So if you have this area divided by this perimeter, then you would get D over 4. But if you have twice as much versus twice the area, twice the perimeter, twice the area, you're still going to get D over 4. So this is a good thing. If they give you a problem, don't go looking at tables to find out what the hydraulic radius is. If they say it's flowing full or half full, go ahead and use that formula. R is equal to D over 4. It'll give you a shortcut. Okay, the Manning equation is used for gravity flow rather than Hazen-Williams, and that's simply Q equal VA, but we have to deal with the slope and the hydraulic radius. Here's the slope, hydraulic radius, and N is the Manning's coefficient, and here, depending on material used, here's all the coefficients. Okay, to find the velocity, to find Q, you'd use this formula. To find velocity, use this. Here's a shortcut for the diameter. Use this formula, and that'll give you the diameter of the pipe you need. Okay, let's look at the Manning equation, and you find Q for a pipe flowing full for a 48-inch reinforced concrete pipe. It's 781 feet long. N is equal to 0.012, and the pipe invert out is 6932. Invert in is 6937. So what is the area? First of all, what is the area for a 48-inch pipe? Just plug that 4 feet in there into the power squared, and you get 12.57 square feet. And R flowing full, D over 4, it's 1 foot, and the S, take the difference in elevation over the length, and you get a 0.007 feet per foot slope. Plug this into the formula, and you get 130.6 CFS. Now you can also do this graphically, where we had a slope of 0.007 feet per feet for 100. Let's go back to this. Here we're looking at 0.07 feet per feet is equal to 0.7 feet per 100 feet. So you go down to the x-axis, 0.7, go straight up, and go to this red line is a 48-inch pipeline. So you go, take the slope up to the 48-inch pipeline, go straight across, and you can see it comes out to be about 130 cubic feet per second. So that's the same as what we got in the formula. Okay, problem number 2. Find the velocity, for example, number 1, where Q equal 130 CFS and A is equal to 12.57. So you want to find the velocity. That's simply Q equal VA, and V would equal 130 divided by that. You get 10.34 feet per second. So if we go back, we can also do that graphically, and where you can see what this is example number 2. That was for a 54-inch pipe. So we're going to take this blue curve up to a 54-inch pipe. That's this other green curve. And we want the velocity, and it hits the velocity right. Here's your velocities coming down. So the velocity looks like it's about 11. .34. So you can look at them graphically, and the graph will get you close enough to the answer in most cases. Okay, find the diameter where Q equal 130 and D S is equal 0.07, N equals that, and D is the inches. Okay, here's where you can go directly to the diameter of the pipe. If you know the Q is 130, N is equal 0.012, and S is equal to 0.07. Plug that into the formula. It comes out 47.9 inches, or the 48 inches. So you can find the diameter of the pipe without going to the graph, just by using that formula. Or you can check it by looking at the graph. Now you can also use what's called an affinity table, where you use the D over D ratios, the Q over Q full and V over V full. And it's better to show you an example, and we'll come back to this table. Let's say you have the 54-inch pipe sewer flowing full, and Q is equal to 179. If Q equal 150, what is the depth D of flow in the sewer? Well, first of all, to use this table, you have to calculate, when you're given the Q, you have to calculate the Q over the Q full. Q partially full over Q full. So coming back here, the Q was 150, and then the flowing full, it was 179, so the Q over Q full ratio was 0.87. Okay? to get the diameter of the pipe, go back to this table, Q over Q full that we calculate is 0.87. We want the diameter of pipe, so we get over here, it's 0.8. So we come back and we simply multiply 0.8 times the 54-inch pipe, and it would be the small diameter of from the base of the pipe up to where it's flowing 150 CFS would only be 43.2 inches. So this is a good way to, you can use the tables in the back of your civil engineering book, and they have these affinity tables that are pretty complex, or you can just use this table. And you can do the same thing with velocity. If you have velocity equal 11 feet per second, Q full equal 179, Q equal 150. What is the velocity? We already looked from the chart that Q over Q full is the ratio of 0.87. And when we go back to the chart for velocity, 8.7, the velocity there would be 1.01. The multiplier 1.01. So 1.0 V, 1.01 versus V full would be 11.1. Okay, wastewater treatment. Now that gets you through all the sewer lines, the gravity sewers and sizing sewers and calculating pump stations, so forth. And those pump stations I gave you, they can be used, those same formulas are used for water treatment as well as wastewater treatment. Here's your water conversion factors for the average design flow for wastewater treatment units would be 100 gallons per capita per day. The peak design flow is usually 1.5 to 4.5 times that average design flow. Now this is the curve from 10 state standards again, and also you have this, they don't give you the curve in the book and your civil engineering book, but they give you this formula. So, and this table is based on population in thousands, and this is the peak factor over here. This is your peak factor. This is your Q peak hourly divided by your Q design average. So I want to give you an example. But look at this population that goes into this formula. This population on the x-axis is in thousands. So just as, well, I think I have an example on that. Okay, if you have a city of population of 100,000, what is the peak hourly flow? Now remember, design sewers are based on an average flow of 100. So first of all, you need to know what the peak factor is. The peak factor is 18 plus the square root of 100 divided by 4 plus the square root of 100. The population is in thousands, so you plug in 100 in both of those formulas. So you have 28 divided by 14 or 2. Now go back to the graph. Population is in thousands. We're looking for 100,000. Go up to the graph, and it's exactly 2 for your peak factor. This doesn't show on yours. This should be your peak multiplier factor over here on the left side. Okay, now to calculate the peak hourly flow, first of all, you have to calculate the average flow, and the average flow is the population times the average daily flow. We use the average daily flow of 100, so 100,000 times 100, and then times the peak factor that we got off the graph or from the formula, and you get 20 million gallons per day, or 20 MGD. Now we're going to look at infiltration inflow before we get into the rest of it, and that's why you have peak factors. A lot of the peak factors, you get your peak flow because a lot of sewer lines leak. And when they leak, instead of having your average dry weather flow, you're going to get infiltration and inflow into the system, and that usually creates your your peak multiplier or peak flow. Some cities have peak flows of 300 or 400% times their average dry weather flow. You can see that infiltration is leaks into cracks or joints into the sanitary sewer lines, whereas inflow would be coming in, it would be rainfall that would be coming through manholes. Maybe you have flooded areas. Certain areas of town will flood, and a lot of that water will go through manholes, or it'll come through other connections. Now, the other connections normally over here, which should be illegal, usually cities have an ordinance that makes this illegal. You have roof drains, and the drains, everything draining off your roof going down through the gutter, should go across the ground. But some people connect that to their sewers, or they connect if they're on septic tanks and their septic tanks are overloaded, they may connect their dishwasher or their washing machine to the sewers, and that would be inflow. That would be illegal discharges into the sewer system. Okay, this is a graph showing infiltration and inflow, and I'm not going into a lot of detail, but basically you have an average daily wastewater flow of 0.74 MGD. So you have an average flow here. The red line shows some of the maximum flows you'd have. So you can see if you have, I'm just going to use an average. Let's say you have an average daily flow of over here on this side. This is the rainfall on this side, the gray lines. But on this side, your average flow is somewhere around, as you can see, 0.74. But you have a maximum daily flow of 2. So if you divide 2 divided by 0.74, that gives you 8 divided by 3. So your peak factor would be something like 2.67. Is that right? So that's how they get peak factors. Okay, here's an infiltration inflow problem. Infiltration is usually limited to 500 gallons per day per mile inch of pipe. And it depends on what size, the diameter in inches the pipe would be. An estimate of infiltration is 10% of the average flow. The average annual design flow of 100 gallons per capita per day includes an allowance for a normal infiltration. The inflows occur during rainfall and shortly thereafter. Okay, let's look at how do you work on an infiltration inflow problem. You have a city of 1,000 population, and it has an average flow of 85 gallons per capita per day. Estimate the average daily infiltration inflow. So the average daily flow would be 1,000 times 85, or 85,000. The estimated daily infiltration flow from this, number 2, and the estimate of infiltration is about 10% of the average flow. So the estimated infiltration flow is 10% of 85,000, or 8,500. Remember, the infiltration flow is going to be a lot less than the average flow, because this is water that seeps through the cracks. It just drips through cracks or drips through joints usually. Now the town above has 15,840 feet of 8-inch sewers. How much infiltration in GPD is allowed, and does the flow in number 1 exceed this limitation? So to get the allowable infiltration in GPD, you're allowed, it's 15,840 feet, and we want to change that to miles, divided by 5,200 feet, 80 feet per mile, because we're using this up here. Multiply it by 500 from this up here, and we're going to multiply that by an 8-inch pipe. So we get 12,000 gallons per day. Okay, the average flow is 85,000 gallons per day. Oh wait, the infiltration. The infiltration is 85 gallons per day. So the allowable infiltration, based on this formula, this is the allowable that cities and EPA will allow. You get allowable at 12,000, but based on our estimate, you only have 8,500, so you're in good shape. You'd have to have, since you're under the 12,000 allowable. Okay, wastewater treatment. Now we're going to get to the wastewater treatment plants, and remember the average flow for design is 100 gallons, but that has to be multiplied by a peak factor unless they give you the peak flow. The actual infiltration inflow is an additional percent. Peak flow multiplier from graph not required with the actual data. So if you have actual infiltration inflow, you use that. If you don't have actual infiltration inflow, especially for a new plant or you're designing a new plant, then you would use the graph. Okay, let's say you have a city of a population of 10,000. It has an additional infiltration inflow of 10%. Remember, that's how you estimate infiltration inflow is usually 10% of whatever the flow, and an inflow of 150%. What is the total average II? And here are the answers. Well, the average flow is 10,000 times 100 would be 1.0 mgd. Infiltration is 10% of the average flow, 0.1. Inflow is 150 of the average flow, 1.5. So the total average plus II is 2.6. So the answer is C, 2.6. If that's on the test, definitely work it because you can work that in a few minutes. This is in your civil engineering book, and it gives you factors. It gives you things like for activated sludge processes, it's based on 1,200 gallons per day per square foot. So that's where I use it. That's where I got the numbers from. This basic chart, this basic regulation. Okay, this is a typical layout, a basic flow diagram for wastewater treatment. You see, for water treatment, the water comes in. The water flow chart showed all blue all the way across, which it usually is unless you after rainfall. For wastewater treatment, every day it's going to be coming. The water's going to be dirty. So you got flow from sewers at 100 gallons per capita per day going through a bar screen, goes into a primary settling tank, and then an aeration tank. Now the aeration tank is the activated sludge tank. Too many people start trying to work sludge problems for activated when you see activated sludge. So we'll get to the sludge problem, but the activated sludge tank is the aeration tank. Okay, if you have these two units, the settling tank, the aeration tank, and the chlorifier, chlorinator, that's a secondary treatment that's required by EPA. If you have to do something more than secondary treatment, then you'd have to have a clarifier. Clarifier is required for tertiary treatment only. And remember, secondary would be 30-30 on the BOD and a total spend of solids. So let's design some of those units. The racks have to be a certain size. I always give the example. I think it was last summer in Chicago. On their bar screen, they trapped an 8-foot alligator that had gotten through the sewers. Of course, somebody went down to Florida and they bought a nice little small alligator, a couple of inches long. But by the time it started to get growing real fast over a couple of days, they probably flushed it down the sewer, or maybe it got larger, put it down a manhole. Anyway, in Chicago, it was in the newspapers, they trapped 8-foot alligator on the bar screen. It was still alive. Okay, the settling tank, you have multiple units are required for flows because you have to have at least 2 units, but you only design for 1. The reason you have to have 2 units is because you get a lot of solids. And these units have to be cleaned out periodically. When you're cleaning out one tank, then you close off a valve, let the flow go through the other tank, through the clean tank. If you get a lot of infiltration inflow, then you can use both tanks in some cases to handle the wastewater. Depth is usually around 10 feet. Overflow rate about 1,500. And the length, again, is about 4 times the width. This is to promote settling, to have that width so the particle will go through a longer to a good length, a much more length than the width would be. This is an old wastewater treatment plant. The flow is coming from the bottom going up to the top. These are overflow weirs that skim floating material, oil and grease off the top, and then that's taken for other types of treatment. And then once it goes through these overflow weirs, you can see there's a divider here, and the scum has been taken off the top, and then the solids settle, and usually in this tank. This may be a shallow tank. Sometimes it settles in both tanks. But this is a real old plant, and it's still working pretty well. Okay, the formula for the calculation of tank size for settling tanks, it's the same formula that we used in water treatment. So when you're looking to size a settling tank, water treatment, wastewater treatment, you use the surface area of the tank, and this applies to a clarifier as well, with the design flow divided by the overflow rate. But the overflow rate will be different for water than it will be for wastewater. So let's say if you have a peak hourly design flow, now if they say peak flow, 2 MGD, then you don't have to multiply by a peak factor if they give you the peak flow. So watch for that in a problem. They say peak, you don't have to, if they say average flow, then you're going to have to come up with a peak flow using that chart that I gave you or the formula, or they may give you the peak flow. So the flow equal 2 MGD, the overflow rate is 1,500, and the length is 4 times the width. We're going to use 10 feet deep. Surface area is the flow divided by the overflow rate. So we have 2 MGD divided by 1,500 gallons per day per square foot, 1,333 square foot. Surface area, the length is 4 times the width. That should be a W. X is W. So 4x squared is equal to that. X is equal to 18. The length is equal to 73. If you want to calculate the volume, the width times the length times the depth, 13,323 square feet. And if you want to calculate the in gallons, multiply it by 7.48 gallons per cubic feet. And what are the dimensions of a settling tank for a city of 10,000 population and a peak 2 times the average flow? Okay, here they're only giving you the population, and they give you the peak, and some people say, well, how do I work that? Well, you take the design flow, 10,000, times the peak flow, times 100 gallons per capita per day, and that gives you 2 million. So if they don't give you the peak flow, you always have to go back to the chart. In this case, they give you the 2, but you'd have to go back to that chart for 10,000, pull off the peak flow. And then you plug it in the formula. Surface area of the tank is 2 million over 1,500, 1.333, and we get the same answer. I just set up the problem a little bit different ways. So they're either going to give you the peak flow right off the bat, or they're going to give you the average flow with a peak factor, or they could give you the population only, and you would have to go calculate the average flow from the population, go back to the graph and see what the peak flow is. Okay, the aeration or the activated sludge process, this is going to remain, and you're going to have a detention time of 3 to 8 hours for conventional activated sludge plants or step or contact plants. Extended aeration would be for a small package treatment plant where the settling tank and the aeration tanks are combined. If you have combined tanks, you have a lot more solids in there when you try to aerate it. Here you've already removed this tank removes about a lot of the solids, the heavy solids, so you only have light solids, and the contact time you only need 3 to 8 hours. But if these two tanks are combined, you need a contact time of 24 hours, a full day. Okay, and you have an aeration rate of 1,500 cubic feet of oxygen per pound of BOD5. This is what an activated sludge plant looks like. You have to have handrails, safety rails around all these, because if you fall in this tank, you're going to sink. You're not going to be able to swim. If you go through OSHA training, you'd go down to the bottom of the tank and get into a crouched position and bring yourself up to the surface. And if hopefully you're close enough to the rail, you have to look for where the closest rail is, move around and crouch again and get to the closest rail. People have died in these tanks because they slipped and fell in. They didn't know how to get out. What you want in this type of tank is you want small bubbles on the surface. This shows small bubbles on the surface. You see a big bubbling arc, like a geyser coming up there in one place. That means your aerator has broken and that would have to be fixed. But you want these small bubbles. You want it to be a chocolate brown color. A tan color means you have too much oxygen or you don't have enough solids going in. A black color means you have too much solids going in or you don't have enough oxygen. This is an anaerobic condition. You do not want the anaerobic condition. It may take days to get rid of it. Tan color is not too bad because you would collect biomass or activated sludge in the bottom. You'd have a separate tank that would take some of the sludge off of this. And if you have a light tan color, then you would add some more solids from the biomass that you've collected from the sludge on the bottom. Okay, let's say you have a 1 MGD plant with a BOD of 200. How many cubic feet of oxygen per day is required for the aeration tank? Now, I'd go directly to this formula that we used before. You have BOD is equal to 8.34 times Q and MGD and C in parts per million. It's a 1 MGD plant, so the Q is, you plug 1 into there. 200 parts, it's 200 milligrams per liter, plug in 200. So the weight of the BOD is 1,668. Okay, the oxygen required, this is from the 2 previous slides, you have to have 1,500 cubic feet of oxygen per pound of BOD, so 1,500 times that is 2.5 million cubic feet. That's for an entire day. So the compressors, you can calculate what size compressor you would need in cubic feet per minute. If ambient air is used, the oxygen is 21% of the air. Therefore, you would need 11.9 million cubic feet of air instead of the 2.5. Some plants are able to generate almost pure oxygen or close to something better than 21%. But if you're pumping right from the air, then you have to calculate this figure because the air only has 21% oxygen. Okay, the aeration tank problem. We're looking at Q equal VA. We're using this basic formula. Here's the derivation of the formula. I'm not going to go through each line. But volume is equal to Q times the detention time. And that same formula, if you remember, we use that for some of the water treatment units. So you use this for the aeration tank. And what is the aeration tank volume in cubic feet for an activated sludge plant with a peak flow of 2 MGD? So you have a peak flow of 2 MGD. Now we're going to assume a 6-hour detention time. Where did that come from? Go back to that table. It's somewhere between 3 and 8 hours is the detention time. So 3 and 8, the average would be 5.5. I just ran it off to a 6-hour detention time. Usually that may be given. If not, I would use a 6-hour detention time. Okay, how do you work that? What's the right answer, and how do you work that problem? Use a 6-hour detention time, and it's simply the flow times the detention time. So 2 MGD, that's the peak flow, times 6 hours, and you have to convert the gallons to cubic feet by dividing 7.48, and you have to convert the hours to days, and you come up with 66.845 cubic feet. Of course, you normally round that off, but it's B, 66.845. Okay, the clarifier. Remember, this is required for tertiary treatment only. Surface settling rate is 1,000 for extended aeration, but for most of the other ones, remember that's for a package treatment plant that would have a 24-hour aeration tank. For most of the aeration tanks you deal with, it would be the surface settling rate would be 1,200. Okay, here's an aerial view of how to lay out a wastewater treatment plant, how to get the best for your money. And if you lay it out like the flow diagram I had, you'd have a narrow, long piece of property. Now, if you look on this side, this is a stream on the right side, and the discharge is right down in here. Okay, first of all, the wastewater comes in above on this above side of the plant, and it goes into what are called carousel or racetrack units. They're really carousel units. And if you notice, some of the units have a lot of froth on the top. Those are the aeration tanks. The one with no froth, they're the settling tanks. So basically, instead of having everything in the horizontal line that would take up a lot of line, it's condensed in a very small area where you have the settling tank and the aeration tanks in that same area. The clarifiers, you have to have two clarifiers. So here's one clarifier, here's the other clarifier. The chlorinator would be here. The chlorine is kept in an explode-proof building here. This is what a clarifier looks like. Now you can't see all of it, but this is usually the bottom of it is kind of a cone shaped on the bottom, and this promotes settling because you have real fine particles that are in here. These are called pin flock. It's a real fine particle that's really difficult to settle out. Your enemy would be floating solids and any type of foaming, because you do get detergents that come through the plant and it causes too much floating. Usually you have to add alum or a long chain polymer to get these small particles to coagulate and settle out. Okay, let's say you have that same flow through of a 2 MGD, that's a peak hourly flow, and it requires a clarifier for tertiary treatment. What is the radius of the circular clarifier? Now here you're given that you have a 2.0 MGD plant. Okay, you don't have to worry about the population. So sometimes it's written, you have an activated sludge plant that's 2 MGD peak hourly flow. So you don't have to worry about population or multiplying by the peak. So in order to solve this problem, you have a settling or overflow rate of 1,200 gallons per day. We're going to use a 10-foot depth. And the formula is the flow divided by the settling rate. That's 2 MGD divided by 1,200, or 1,667 square feet. Surface area is the area of a circle, and you get a radius of 23 foot, and we're using a 10-foot depth. And we're assuming that this is a cylindrical rather than a cone, because a lot of them are cylindrical for the effective depth, and then they have the cone below that. But they would have to tell you that on the test. So if we assume that it's cylindrical before it gets to the cone or the settling tank, then it's the 667 square feet times 10 feet depth would be that, and that would be, what's the nearest one? What the question asked for. We have to go back and look. What is the radius of the circular clarifier? And I gave you a bunch of extra things there. And be sure that you read what they're asking for, because they'll say, what is the radius in feet? And on the test, they won't give you feet over here. They may only give you a number. So you have to read the problem, make sure you're going after the right answer. It'll usually be stated, what is the radius in feet? And then they won't have feet in the answer a lot of times. So here, the answer for the radius was 23 feet, and that would be E, 23. Okay, the chlorinator. Chlorinator, we're looking at a 15-minute contact period for wastewater treatment. It could be more than that if you're not getting the proper 30-30 for the BOD and the suspended solids, then you may increase it 15 minutes. But assuming you're getting 30-30, then 15 minutes is usually the time. If it goes to a tertiary plant, you'd only need 6 milligrams of chlorine because the water will be real clean going in. For a secondary, it's usually 8. This is how much chlorine you add. 6 milligrams for a tertiary, 8 for a secondary, and 10 for the extended air. And what is the volume of the chlorinator for a 10 CFS peak design flow wastewater treatment plant? Okay, if we go back, we're given a detention time of 15 minutes, so we're going to use, you got 2 formulas to use for wastewater and water. One is equal to volume is equal to Q over TD, and the other one uses the overflow rate on the bottom. So with this one, volume is equal to 10 CFS times 15 minutes times 60 seconds, converts the minutes to seconds to cancel out the cubic feet per second, and you get 9,000 cubic feet. That would be C. Now, these problems that I give you, were these actual questions on the test? No, because I'm not going to be doing that, but the numbers may not be the same, but they may be similar. Okay, looking at the water quality that goes to the stream, you want 30-30 for secondary. Tertiary, you want the solids to be 20 milligrams per liter, BOD to be 20. Advanced treatment would be 10-10. Also, you check for toxicity because you don't want anything toxic going out into the stream, because this just covers the actual human wastewater, and it doesn't cover any toxicity that may come from industries in the area. So to make sure you're not having heavy metals and some other things that would kill the fish, then you'd run a toxicity test. And basically you collect a sample of the discharge and you dilute it to the stream dilution back in the laboratory, and you put so many fathead minnows, so many water fleas in there, and over a number of days, if the life cycle, if you have at least 50% of them left in the tank, then it's not toxic. If you have less than 50%, then the city would have to go back in and find out what industry or what's causing the problem. Okay, now we're talking about sludge treatment. This is not activated sludge treatment. This is the sludge that would accumulate in the bottom of the settling tank or the bottom of the activated sludge tank or the bottom of the clarifier. So whenever they have to clean it out, they clean that sludge out, and that sludge has to be treated. Okay, this is from the 10 state standards. And normally you would have a secondary, which would be a primary settling tank plus waste activated sludge. Now remember, the waste activated sludge is not the sludge you're treating here. This is from the aeration tank. So it's from the settling tank and the aeration tank. So people get confused when they see that. So that would be a factor of 4 cubic feet per population equivalent. Okay. Now this is for an aerobic treatment tank where they would put the sludge in a small circular tank and add air to it over a number of days until the sludge is reduced, until the bacteria reduces the sludge. So it's not activated sludge, it is the separate tank that's not shown on the flow diagram. Sewage sludge is normally treated by aerobic treatment. Some people have used anaerobic treatment to collect the natural gas if it's a large enough plant. Sludge drying beds require 2 square feet per capita. Vacuum belts are also used to dewater sludge to reduce the volume, so you don't have to go through, after you treat the sludge with an aerobic treatment, then you usually run the sludge over vacuum belts, and then that's put in a dump truck, and it looks pretty dry at that time. That treated sludge can be disposed of in a sanitary landfill. And speaking of sanitary landfills, you'll see a chapter in the wastewater chapter at the end. They have topics on sanitary landfills and hazardous waste. That is not on. That will not be on the civil engineering test. That's on the environmental engineering test, but you won't have any problems on sanitary landfills or hazardous waste. So don't study that for your test, even though it's in the civil engineering handbook. Okay, what is the volume of a aerobic treatment plant for a 2.2 MGD plant? Going back to this table, remember it's 4 cubic feet is required for each population equivalent. So if we go to this problem, a 0.2 MGD plant would have an equivalent population of 2,000. The equivalent 0.2 times 100 gallons per day. This is average. We base it on an average when we're talking about sludge instead of peak. It'll be a 2,000 population. So the volume of the aerobic digester is 2,000 times 4, and that would give you need 8,000 cubic feet for the aerobic digester to treat sludge. For the drying beds, if you don't run it through a vacuum belt, you'd need 2 square feet of drying beds per capita. So 2,000 times 2 square feet, you'd need 4,000 square feet of drying bed. I've seen on the internet that people, after they took the test, they saw a lot of sludge problems. And this is what the sludge problems are. They're not that complicated. But you also have activated sludge, which is really aeration. So you're talking about different things. So people that aren't familiar with wastewater treatment, don't get those two confused. Okay, water quality. Now this gets into the appendix, but we still have 10 minutes. There are a couple of questions on here that even though you're a civil, you may have a question on some of these in the morning because some of them are fairly simple, and they are in your civil engineering book. So I've already been through the purpose of protecting the water. This is in the Clean Water Act. And usually the waters are sampled for these. These are indicators of good water quality. Sometimes this is asked. I've seen it asked in some of the example test questions that you can buy and answers. What are indicators of good quality? Stonefly, mayfly. If you're getting black fly larvae, that would be an indicator of poor water quality. Okay, for water quality sampling, for a wastewater treatment plant, if you're sampling the stream to see if your plant is not polluting the stream, you need one upstream sample and one downstream sample. For groundwater, you need a minimum of one background sample, or this is up gradient versus the low elevation of the stream, and 3 down gradient samples. So this would be a background, this would be above, because you may have industries or other sources that may pollute the groundwater here, so you need to sample here to see if you're getting pollution from above. So at a minimum, there's one up and 3 down, or a total of 4. For groundwater, that's always the case. So if you have a problem, let's say you have a treatment site's bordered on the east side by one stream and on the west by another stream, how many water quality monitoring stations would be required if discharges are to both streams? If you're discharging to both streams, you have to have 1 up and 1 down for each stream, so it'll be a total of 4. Let's say you don't have any of the streams adjacent to the treatment site. How many groundwater monitoring stations are required? You always need a minimum of 4, 1 up and 3 down. Because you're sampling groundwater, you're not sampling surface water. Okay, to calculate BOD5, and I'm not going to spend a lot of time on this. It's a chemistry problem that you run it in the lab. You can go through this, but basically you're going to take 10 milliliter samples and put them in the 10 300 milliliter bottles, and then you're going to put distilled water of 290 milliliters, so you have a total of 300 milliliters. And then you're going to take 5 of the bottles and titrate them and immediately sample them for dissolved oxygen. You take the other 5 bottles and they're incubated for 4 days under a little bit warmer temperature, and they're gently shaken periodically. And this is why it's called BOD5, because the samples are incubated for a 5-day period. So whatever the DO is before you incubate them, that the average of the 5 samples that don't go through incubation, you can see that the DO goes from 7.1 to 3.7 after it's incubated. In other words, the biochemical oxygen demand, or the bacteria, use up 3.4, the difference of these two of the oxygen. Then the volume of the sample that you're putting in there is only 10 milliliters of wastewater. The total volume, the sample plus the dilution water, is a total of 300. That gives you a BOD of 102. BOD of 300 is considered a strong effluent, and 250 is considered medium, and 100 is considered weak. So usually if you have a BOD of 100, your wastewater treatment plant may not work too well. If you have 300, it may go anaerobic. Okay, to calculate how that wastewater treatment plant would affect the stream right after it hits the stream, not a 7-day DO sag curve, but to use the dilution formula. And it's basically the plant discharge, Q, 15 CFS, and 45 BOD. Plug that into that formula, C1, and then the stream has BOD of 4. That's from the fish and the dying bacteria in the stream. And the stream has a flow of 120. Add the flows of the flint, and you get an 8.56 BOD in the stream. So in other words, the stream was 8.3. After you discharge the wastewater into it, it becomes 8.56. You do the same thing for DO. You use the same flows, but you just plug DO and you come up with a DO of 7.7, whereas the DO was, I was wrong. The BOD was 4 in the stream, and it went up to 8.56, so it doubled. But the DO was 8.3, and it went down to 7.7, which is not too bad. Okay, hardness. Hardness is mainly, this is a typical question that all civil engineers may have to answer. There's a shortcut. You have this in your civil engineering manual. But hardness would be the metallic ions or the plus ions that causes hardness. Common ones are magnesium, calcium. Some places have iron, some places, but magnesium, calcium, you get enough magnesium and calcium in drinking water from treatment plant where you don't have to take vitamins for those. And then the negative ions would be the alkalinity. So let's go to a problem on that. This is straight from the table of the civil engineering manual. And calcium and magnesium and iron are pretty common. Aluminum is also common. for the hardness, and then I've underlined the ones that would cause alkalinity, the negative. So these are factors you use that you multiply by the concentration to come up with a hardness value, which is expressed as calcium carbonate. You can go through the chemistry, but this is a lot easier. So I pulled out, here's a problem where you have so much aluminum, calcium, iron, and magnesium. I pulled off the factors from that table. These are all plus factors. These are the factors for each one of those that comes from this table. For example, aluminum is 5.56. Then all you do is multiply the concentration of aluminum, 0.5, times the aluminum factor, 5.56, and that's 2.78. Multiply the calcium, which is 80, times the factor, and you get this, and you go on out. You get a hardness of 300. Anything that's over 100 is considered extremely hard. Is hard. 300 would be extremely hard water and would have to be treated. Some of the chemicals that are used to knock out, to correct the problem, is alum, and I think I mentioned to you, during periods of high turbidity, you would add alum to the mixing unit or to a wastewater treatment plant if you want settling. So alum promotes settling. You add that to clarifiers. Long-chain polymers are added to clarifiers to promote settling, and sometimes they work a little bit better than alum. For water softening, you add lime to remove calcium and magnesium. So in a water treatment plant, that's why you add lime during the typical dry weather flows. And you'd add 10 to 50 to help knock out the calcium and the magnesium, which is hardness. So you're adding lime to knock out hardness. If you have sulfates and chlorides or negative ions or alkalinity, you add soda ash. Okay, to knock out taste and odor, if you have sulfides, H2S, you'd use aeration. Activated carbon is to remove taste and odor. And chlorine will help also oxidize odors. I think I mentioned this before. Some people say, well, why don't you just use ultraviolet light and forget about chlorine? Well, if you use ozone and ultraviolet light, you still have to use some chlorine after that to keep the residual, because you have to maintain a residual of 0.3 or less to make sure you're killing bacteria in the water distribution system. Okay, that's the last slide, and we got like 1 minute, and I've got a lot of questions. I'm not sure if I can answer all these in 1 minute. Wow. I'm going to see if I can combine those, but there's no way I can answer these now. We'll print these out, and if you have any if you have a question, go ahead and email me. But when you ask the question, say on slide number so-and-so, make sure you mention the slide. Because some of these you don't have the slide number, like there's one that says, a lot of these questions, just make sure you mention the slide number if you email, and I'll try to answer that. So good luck on the test, and hope to see you as a PE.